We're about to have a whistle-stop tour of some of the world's key blue carbon habitats from experts in their field. But first, a little bit of perspective. Looking back on history, what could we really achieve with blue carbon if we were to restore the ocean ecosystems to their full potential? In setting our baselines, are we starting from the right places, or could we achieve more?
Marine science is a young discipline. The first major oceanographic expeditions were in the late 19th century. Direct underwater observations using submersibles and scuba only became commonplace from the 1960s on. But there is a much longer history of human disturbance and impact that predates these observations. Marine science therefore suffers from shifting baseline syndrome. The first scientists to observe and measure the seabed and its life mistakenly assumed what they found was the product of natural rather than human processes. The assumption of the dominance of natural over human agency in shaping marine habitats continues to this day. By focusing on present-day habitat states and ecological processes, we may miss much that is important. The first omission is to assume that because measured rates of carbon uptake are low today, they will always remain low. But what would happen if we really protected the seabed? Far from being the monotonous stretches of shifting sand, mud and gravel that predominate today, historically the seafloor was a patchwork of rich and extensive seaweed stands and dense invertebrate communities like oyster and mussel beds, collectively known as marine animal forests. The removal of these animal forests by trawling likely profoundly altered the movement, capture and storage of seabed carbon, just as a landscape denuded of vegetation loses soil. By reversing long histories of loss and degradation, protection could recover the capacity of ecosystems to take up carbon once again. The second mistake is to assume that present-day rates of carbon capture accurately reflect the value of a site as a blue carbon project worthy of protection. The example of the North Sea's Dogger Bank is telling here. Measured rates of carbon deposition are low today, but the Dogger hides thick peat deposits laid down as the ice retreated thousands of years ago. 19th and early 20th century accounts eloquently describe the destruction of peat by bottom trawls. There is still peat on the Dogger today. How much and how vulnerable it is needs urgent investigation. Protection of peat on land is taken for granted as sensible climate policy, yet peat deposits underwater have been completely ignored. We must put them on the map. In folding blue carbon into plans for better ocean protection, we must think beyond what is in front of our eyes. Let's imagine instead, what could the sea offer if we did things differently?
Mangrove forests are a key component of the blue carbon landscape. Due to their anoxic soils and high productivity, they're able to sequester almost 4 times as much carbon per square meter per year as other terrestrial ecosystems. And even in disturbed and fragmented mangroves such as this one in Singapore, it's still able to store more than twice as much carbon per hectare as our neighboring tropical rainforests.
The fact that they are so efficient at storing carbon also means that mangrove loss can make a disproportionate contribution to carbon emissions. This is happening as we speak, as mangroves still continue to be lost at 0.1 to 0.2% per year, with Southeast Asia a particular emissions hotspot. Altogether, this creates a real incentive for mangrove blue carbon conservation. Mangroves have played a key role in driving forward the implementation of blue carbon projects, and an increasing number of projects have been established in Kenya, Madagascar, and most recently in Colombia. The Colombia project alone is estimated to remove more than 1 million tons of emissions over the 30-year project timeline.
These projects are just the tip of the iceberg, and the global opportunities are huge. Our recent analyses suggest that about 20% of the world's mangroves will qualify for some sort of avoided deforestation blue carbon project. And for 10% of the world's mangroves, these projects are estimated to be profitable.
Important opportunities also exist for the restoration of mangrove blue carbon. As much as 800,000 hectares of former mangrove areas around the world may be biophysically suitable for restoration, and countries such as Indonesia have ambitious near-term restoration targets. The carbon returns from mangrove restoration can be substantially higher than terrestrial carbon projects. A mangrove restoration project in Sulawesi was able to sequester between 20 to 60 tons of carbon per hectare per year, compared to an average of 10 tons for other verified terrestrial carbon restoration projects. This provides a great opportunity to produce a high density of carbon credits for local communities. But to make the most of this opportunity, we need to work a lot harder to improve the success of restoration, which requires planting the right species in the right biophysical location, fixing land tenure conflicts, and incorporating local communities into project planning and implementation. And of course, as with all blue carbon ecosystems, protecting carbon also protects a vast range of other benefits, including fisheries, coastal protection, and products that support the livelihoods of coastal communities. This is the real power of blue carbon conservation.
Mangrove blue carbon has gained huge momentum from both government and commercial stakeholders. If we can capitalize on this interest, then we'll be able to safeguard the future of this resource for millions of people across the tropics.
Seagrass meadows are moving beyond their identity crisis. The once ugly duckling of the conservation world is now becoming the beautiful swan. The world is now slowly waking up to the power of this group of humble marine superplants as a kind of part of this complex jigsaw of how we fight climate change. The beauty of conserving and planting seagrass to fight climate change is that it doesn't require buying expensive land, and it doesn't displace current farming activity. In fact, it promotes food supply through the creation of essential fish habitat. Just like trees, seagrasses are all different. They have the equivalent of the slow-growing epic redwoods, such as the posidonias, and they also have the fast-growing equivalent of the pine forests with the halophilas. When we translate these differences into rates of carbon storage as a mean to fight climate change, just like the world's forests, we get lots of pros and cons in different scenarios. Understanding the capacity to translate these different seagrasses into engines of carbon storage comes down to three key elements: opportunity, rate, and scalability. And all these factors are modified by our knowledge gaps in these systems. The zostras sit somewhere in the middle of that range from Posidonia to the halophilas. The opportunity for the zostras is that their coverage has been decimated, mostly over the last 100 to 200 years. The recovery of these environments creates that huge opportunity, that opportunity that's needed for restoration in terms of creating new carbon sequestering habitats. There's still a lot of knowledge gaps about the rate and balance of greenhouse gas emissions of the zostras, but evidence does indicate it stores somewhere between 0.5 and 1.5 tonnes of carbon per hectare per year, even within restored meadows. These rates are highly comparable, if not a lot better, than other so-called nature-based solutions. Importantly, these rates can be achieved rapidly as a result of restoration, and the associated methane and NOx emissions are comparably also very low. But we do need to more mechanistically understand what drives the net accumulation of organic carbon so that we can improve conservation and restoration to enhance and maximise those rates. Finally, scalability. Can we actually take the restoration of the zostras to a whole new level? Well, Professor Bob Orth and his team in VIMS have actually already demonstrated this unequivocally. Seagrass meadows can be restored at sufficient scale to transform the delivery of coastal ecosystem services. Fisheries can be rejuvenated, carbon storage expanded and biodiversity enhanced. We now need to build on that experiences of scaling seagrass restoration from the US and use some of the great science that's coming out of places such as Sweden, the Netherlands and Australia, and apply it across the temperate seas. At Project Seagrass and Swansea University, we're also using that knowledge and also learning ourselves about how to scale up seagrass restoration. But we need regulators, funders, marine stakeholders to get behind that push to enable seagrass to fulfill its potential to be this beautiful swan of marine conservation. Thank you.
Seagrasses are a vital tool in nature-based carbon capture, with additional co-benefits in coastal defense and supporting marine biodiversity. The seagrass Posidonia oceanica is endemic to the Mediterranean Sea. It develops extensive meadows where long-term carbon burial is on average at 63 grams of carbon per square meter per year. That's 15 times more than a tropical forest. This buried organic carbon can be preserved for millennia, developing carbon deposits up to 6 meters thick. As a result, the top meter of Posidonia oceanica soils store on average 370 megagrams of carbon per hectare, more than the amount of carbon stored in forests. These intense natural carbon sinks also help coastlines keep pace with current rates of sea level rise, as the build-up of carbon-rich soils in the seagrass meadow effectively rises the level of the seabed as sea level rises. Meanwhile, the meadows themselves help prevent coastal erosion, making them highly effective coastal defense structures and thus a key ecosystem that we need to protect in the context of our range of blue carbon solutions. Since the end of the 19th century, areas of Posidonia oceanica meadow have been reduced by between 13% and 15%, mostly as a consequence of local disturbances, with loss rates peaking between the 1960 and the 1980. Since then, conservation and environmental policies and interventions have decelerated the overall rate of loss, but the extent of historic meadow cover is far from being recovered. This is due in part to the slow growth and recovery rate of the species. Posidonia oceanic seagrass remains an important tool for carbon sequestration, as well as delivering significant co-benefits for biodiversity and coastal defenses. Any further blue carbon projects should aim to remove local pressures, avoid further losses, and promote restoration and recovery of these wonderful underwater meadows across the Mediterranean.
Habitats of macroalgae, also known as seaweeds, play a substantial role in marine carbon sequestration. They also support biodiversity by providing food and substrate and shelter for a wide range of organisms. Macroalgae are a very diverse group encompassing both brown, red and green algae, which are as remotely related as fungi and elephants. They also differ greatly in size. The leathery brown kelps are the largest and include giant species exceeding 30 meters in length. Macroalgae form by far the most extended and productive of the vegetated blue carbon habitats, and they occur in all climate zones. Recent overviews suggest there are about 7 million square kilometers of these hidden forests globally. While mangroves and seagrasses and salt marshes are rooted on soft or sandy seafloors, macroalgae dominate rocky substrates which do not sequester carbon. But macroalgae export much of their biomass as particulate and dissolved carbon, and it is estimated that 11% of their production reach carbon sinks in shelf sediments and in the deep sea. This amounts to a global sequestration of about 173 teragrams of carbon annually. The role of macroalgae in blue carbon strategies is still controversial, largely because of the challenges in documenting and quantifying the carbon sequestration beyond the habitat. But there is no doubt that the protection and restoration of macroalgae and their carbon sinks around the world will increase their blue carbon potential.
Seaweeds have been a part of our food system for centuries and are used today for edible products, animal feed, and commercial gels. They're a low carbon footprint ingredient that could also be part of a carbon dioxide removal strategy to address climate change. Worldwide, 221 species have economic value, but only 10 of those are intensively cultivated in the ocean. 50 countries now grow roughly 30 million tons of seaweed in total each year. In fact, the seaweed sector is growing so rapidly it is projected to surpass global potato yields by the year 2050. Like plants, seaweed take up carbon as they grow. We are also learning that seaweed shed biological matter, a fraction of which may get buried in the sandy or muddy ocean bottom below a seaweed farm, sequestering the carbon within the marine sediments. But we don't know exactly how much matter each species sheds naturally, or how predictably ocean currents redistribute this matter. If early estimates are correct, roughly 11% of farm seaweeds could eventually become permanently buried beneath the seafloor. In that case, seaweed farms might sequester approximately 1.5 million tons of carbon dioxide today. And as the industry grows, up to 41 million more tons may be sequestered each year in the future. It has been proposed that instead of using the crop, sinking these seaweed farms to the ocean floor could maximize their sequestration potential by burying all the carbon they capture. However, the carbon cost of moving and sinking large amounts of seaweed offshore and its ecological consequences are unknown. In addition, this would impede production of a nutritional food source and a versatile crop in a time of growing global populations. Therefore, it is urgent that we understand the potential risks and carbon costs associated with sinking farmed seaweed to the seafloor, versus exploring the crop's full potential as a climate-friendly product in bioplastics, organic fertilizers, animal feed, and other innovative products.
DEEP is the Dornoch Environmental Enhancement Project. It's a partnership between Glenmorangie, Heriot-Watt and the Marine Conservation Society. And overall, DEEP seeks to restore native oysters to the Dornoch Firth. We've studied the oyster populations in the Dornoch Firth and we found evidence that oysters were present right from the last glaciation 8 to 10,000 years ago, all the way up to about the 1800s when they were probably fished out like they were everywhere else in Europe. Oysters are really important because they have ecosystem functions. So they're not just important for their biodiversity, they're also important for their blue carbon, the carbon that they deposit onto the seabed. They're important for improving water quality and providing habitat for potentially commercially important species. So businesses are increasingly interested in not just the biodiversity value of restoration, but the other services that these habitats provide. And in the DEEP project, we're very much interested in biodiversity, water quality, and increasingly blue carbon.
When we consider the oyster carbon picture, we can look at it a bit like a jigsaw. There's different components, and you need to measure all of the different parts to get the full overview. Oysters are filter feeders. They filter out food, sand, mud, carbon-containing crud from the water, digest the most nutritious bits, and deposit what's left down onto the sea floor as oyster poo. During this process, they also can enhance water clarity. Then you have the oyster shell. It's made of calcium carbonate. The process of calcification captures a bit of carbon and also releases some. There's also a release during respiration. So by looking at the full picture, we can start to discuss whether an oyster bed is actually drawing down carbon or if there is just an accretion of carbon. So whether you've got a case for climate mitigation here or carbon storage. And then past that, you have the fate of the carbon for the future, whether it's disturbed, bioturbated, or eroded.
What we're interested in really is the carbon that's here to stay in these habitats. The key challenges that we have going forwards is how to keep these habitats undisturbed and protected. And if we can do it here, we can do it anywhere else.
I'm standing on a salt marsh in North Wales. Behind me you can see a sand dune, and beyond that there's mudflat and the Irish Sea. In addition to being beautiful places in their own right, salt marshes play an important role in flood and coastal defence and support many rare and important plant and animal communities. Salt marshes are also highly effective stores of carbon, capturing suspended sediment rich in organic matter and locking away carbon over the long term in deep muddy deposits. The marshes can also respond to changes in sea level as they build up vertically. Recent studies have found that up to 40% of carbon stored in salt marshes is derived from terrestrial material, some of which could otherwise have been lost and oxidised as CO2. Globally, salt marsh soils accumulate organic carbon at a faster rate than soils of terrestrial systems. Although in some cases it can be much higher, average carbon burial rates for terrestrial forest systems range between 4 to 5 grams per metre square per year. In contrast, globally, salt marsh soils can store organic carbon at a rate of 218 grams per metre square per year. In addition to the high carbon accumulation rates found in existing natural marshes, even greater long-term carbon storage can be achieved relatively easily by creating new marshes. With a relatively simple breach in existing coastal defences, allowing flooding of former salt marsh drained for agricultural land, tidal ingress allows large carbon-rich deposits to settle out quickly and easily. These deposits could be considerable, up to 1 metre a year in the initial stages at some sites. In just one salt marsh restoration site in the UK, estimates suggest an incredible 30,000 tonnes of carbon were sequestered in its first 5 years. Salt marshes have a global distribution and are increasingly seen as a useful nature-based solution with an important role to play in our battle to mitigate climate change. Not forgetting they are also delivering significant cultural, economic and biodiversity benefits. We need to bring experts together, from practitioners to policymakers, from artists to economists, and just see how far we can get with this approach.
The seabed is the ocean's ultimate carbon sink, fed with organic matter through the entire biological pump. Globally, subtidal seabed sediments are estimated to store up to 3.1 teratons of organic carbon in their top 1 metre. This is over 11 teratons of CO2 equivalent, more than twice that of all terrestrial soils combined. This carbon is most concentrated in near-coast areas, particularly in muddier sediments, in upwelling zones and within fjords and estuaries. Much lower concentrations are found in deep basins and abyssal sediments, but due to their large area, these zones make up the dominant carbon store of the ocean. Global estimates of sequestration rates are in the range of around 130 to 350 million tonnes of organic carbon per year, which is equal to up to 1.3 gigatons of CO2 equivalent. This is an average of only 0.04 tonnes of CO2 per hectare per year. However, dependent on the environmental settings, local sequestration rates can reach up to and above 3.2 tonnes of CO2 per hectare per year. The sequestration of carbon in seabed sediments requires a healthy functioning ecosystem at a whole seascape scale. One way to promote carbon sequestration would be to increase primary production at the surface, such as through seaweed aquaculture, vegetated habitat restoration and improved water quality. We must also reduce our impact on the wider biological pump, striving for healthy, diverse invertebrate and zooplankton communities and maintaining fish and marine vertebrates at higher population sizes. However, due to the relatively low annual sequestration rates mentioned earlier, avoided emissions by the removal of disturbance from stored carbon far outweighs the climate mitigation potential of promoting sequestration. A recent global estimate calculated that bottom trawling and dredging may release between 0.6 to 1.5 gigatons of CO2 into the water column each year. This is a similar amount released into the atmosphere by global aviation each year. More evidence is urgently needed to more accurately quantify this impact of physical disturbance on seabed carbon and incorporate full, evidence-based carbon considerations into global seabed management. If handled correctly, blue carbon in seabed sediments could unlock major carbon financing opportunities and huge climate change mitigation potential. This should be done by implementing full protection of stocks, while allowing recovery and potentially restoration at the scale of whole seascapes, not small fragmented pockets.